Hi there, my name is Nasali Catherine, and we are going to take you through our Tyre Safe detection application. And yeah, tires are significant when it comes to security on roads. These defects that appear on them, for example, cracks and punctures, they they pose a serious risk to drivers or riders on the road. We look at traditional inspection methods used these days. They are slow, prone to error, and they are they are not automated. So if we look at automating this process, it could lead to having quality control and things over like that would make tire defect detection much safer for drivers. Yes. When developing this project, we had a few things in mind. First of all, we want to create a hybrid model that uses a number of machine learning methods, for example, generative adversarial learning, contrastive learning, and knowledge distillation for real-time tire defect detection. Secondly, we wanted this model to have an accuracy above 90 when it comes to classifying defects. Then we want to reduce accidents and costs by enabling early defect detection. This model should be scalable, lightweight, and deployable on constrained devices. Yes. Our approach on this was that we wanted to generate synthetic defect or tire images to address data scarcity. Well, luckily enough, we were able to land on a good data set with enough photos. So the cyclogram struggled a bit, but we explored both cyclogram and BCGANs. We used contrastive learning. Most of our models, or we could say like 90% of the models we have right now, we trained, they used contrastive learning to distinguish normal tires from defective ones. Then we also explored knowledge distillation from where a complex model, a teacher model, trains a smaller, lightweight student, for example, the mobile vignette or the custom CNNs, to make defect detection much simpler or easier. Yes. I previously talked about the dataset we used, and would like to thank the Mendeley team for providing us with images. They had 828 good tires and 1028 defective tires, which captured various features, for example, trends, the quality of the rubber for the good tires. And when it comes for the defective, we had a variety of defects, for example, the cracks, wear, yes, like how you could see in the pictures there. Yes, for the images that we got from this dataset, we preprocessed them. That included resizing them, converting them to a certain scale, and normalizing the pixel values. So we extracted features. That was for the EDA analysis. Then we trained 10 models based on what we had before. So the 10 models, we had the models that stood out. For example, the ResNet 80, the MobileNet V2, and yeah, the Random Forest model as well. When it comes to evaluating these models, we used accuracy, F1 score, precision actually. Then when it came to explanatory AI, we performed explanatory AI for the 2 best and 2 worst models, yeah, for interpretability of how these models worked. So what was our system architecture? While training, we looked at data processing and preprocessing, the preparation and preprocessing, and then from there we extracted the features. From extracting the features, we looked at the actual learning process, which included using synthetic image generation, contrastive learning, knowledge distillation, and after this training, we looked at optimization of the models that we had, then evaluation and validation, and lastly, we deployed the model that was the latest. Yes. So here, what we did was that we got our tire images, as you saw from Mendeley dataset, we resized them, and then we prepared them for analysis. So using the mobile V2ness as a study case, just know we studied the images and we made it into a binary classifier to know if the tire is good or defective. So we fine-tuned this model, and after fine-tuning the model itself, we trained it on pictures, and it is stopped early to avoid wasting time. And we checked this model using accuracy the balance of how correct its guesses are. And then we also tested it using the pictures. So we saved this model later and we deployed it, and its features final scores were recorded. Yes. So Matthias is going to take us through the rest. Thank you.
As you can see in this table here, we have the results from the training process. We have the models 1 to 10 of them. Yeah, the mobile net v2 has the highest accuracy of 93.58, and the contrastive learnings as the lowest, which is 55. Then the other side, we have the explainable AI, the mobile VNet, and we tested the different aspects of silence maps, counterfactual, and then Lime explanation, sorry. And then here we have the impact and relevance of the model. So our model is going to be used in different sectors. For example, we can use it in manufacturing, can use it in auto services and repair, we can use it in traffic, we can use it in a toll. Personally, I can use it if I don't like I have my vehicle and I need to check the tires to see that whether they have no faults, I can be safe on the road. So to save people's lives, this model can be very helpful. Then the intellectual property and innovation. Yeah, so the potential intellectual asset here we have is our algorithms. Yeah, we came up with hybrid approach algorithm using first generative adversarial contrastive learning with knowledge distillation. So these help the model to improve the model and so on. And then the patentable, our model is really patentable because we actually came up with something new in our knowledge distillation where we're able to merge a few other techniques to come up with a better model. Then the copyright, yeah, I think the code implementation and documentation can be cooperated to protect a specific expression of the solutions. Then monetization scaling. The revenue streams here we can use subscription fees. Large companies, like for example, auto service companies, they can use licensing service fees and then pay pay-per-use API. In customer segments, we have tire manufacturers, fleet operators, automobile service, then acquisition strategy. People can actually acquire through the Excel, they can acquire through online platforms. Then the scalability. Scalability here we mean how the model will be actually used, whereby someone can scale it up and down. Then the funding readiness. Here we shall seek funds from different organizations such as government organizations and USAID. So a system demonstration. Yeah, as you can see from my background here, we're actually running a demo of the system and how it works. Here you upload an image and then you wait for it to load, and then you click the predict button to be able to show you the output, whether the tire is good or defective. As you can see, the tire was loaded, it was a good tire, so the prediction was good. Then the team contributions, this actually shows the contributions from me and my teammate Nasari Catherine. Yeah, and demonstrates our contributions from the dataset, our concept paper, EDA, and all that. Then the lessons learned and challenges. So some of the challenges were we had difficulty in actually developing a cycle gun model. We had a difficulty in deploying since the model was large. And then we also had a difficulty in over high resolution images. They were a bit hard to walk around with. So the lessons we learned that using hyperparameter tuning helps you to improve the model results and come up with more accurate results. And then the use of the more you train the model when you use high epoch, and be able to actually develop better models as the model gets familiar with the images, and then can be able to develop something good. And the future works. I think focusing on the limitations, we can be able to get some resources and be able to come up with a cycle gun since it actually develops more clear images than the vanilla gun. Then the conclusion, basically using our model, we're able to develop hybrid models that incorporate contrastive learning, distillation, and generative adversarial learning, which improve the image classification and quality. And then the project I think model enhanced to help out in effective and efficient detection industries has saving time. So in short and a bit of a conclusion, so the model that the study this or the project using these different architectures of the training can be able to improve accuracy, efficiency, and defect detection within the industry of tires, and also in other applicable areas like auto service centers and then government inspections. Thank you so much.